Welcome to Stable Sort. In this episode, we're going to discuss Knuth Morris Pratt string searching algorithm. Now, I'm going to assume that you already know all about the brute force way of searching for strings. After all, everyone and their grandma already knows how to do that. So I'm going to jump straight into explaining how the KMP algorithm works, go over a sample implementation of it, and derive its running time. Suppose we have some long text that starts with characters A followed by a bunch of B's, and suppose our pattern string is A, B, 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 C. On our first attempt, we match the characters one at a time, eventually get to the C character where a mismatch occurs. The question now is, for the next attempt, do we shift the pattern string by just one position, as is done by the brute force algorithm? Or can we shift by more than just one position? KMP algorithm is very clever, and for this particular pattern string, it restarts the matching right at the index where the mismatch was encountered, shifting over by 4 positions. So how could it do that? How does it know that a match could not possibly be made if starting the matching process anywhere in that first section? The main insight here is that the characters at the beginning of the pattern string itself need to be repeated in order for that possibility to exist. If the characters at the beginning of the pattern string are not repeated in some other place of the pattern string, then it's safe to skip ahead on each mismatch. In our example, the first character of ABBC is the A character, and it does not appear anywhere else in the pattern string. Since we matched on characters A, B, 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 we therefore know that the text does not have any other A characters in that section. So we can skip ahead by however many characters we did match in the last attempt. The last attempt matched 4 characters, so we can shift the pattern string forward by 4 positions. Let's take a look at this more carefully and develop a more general solution that doesn't hinge on just the first character being unique. For the next example, we'll use a different pattern string, ABC, XXX, ABC, Y. Before doing any matching, the algorithm prepares a separate array that stores the length of the longest prefix that occurs throughout the pattern string. This is easier to see and understand than to define. The characters ABC at the beginning of the string are also found towards the end of it. They are highlighted for clarity. So we'll be looking for a pattern where the first character is A, followed by B, and possibly more. For the first character, we define the length of the prefix to be 0. For the second character, B, since it does not repeat the start of the string, the prefix length is set to 0. Same is true for all the subsequent characters until we find another A character. The length of the prefix at that point is 1. The following character B extends the length of the prefix to 2. The next character C extends the prefix once more to 3, but that's where the match ends. The character Y does not continue with the prefix, so the longest prefix value becomes 0. By the way, the prefix length at index 0 is -1, and this is just for convenience. Some implementations don't actually require it. This array is used to calculate how far forward we can shift a pattern string. A value of 0 means that we can shift forward by the full amount of however many characters we did match in the previous attempt. So zeros are our friends. They signal that we can shift forward by the most amount possible. But if there are repeated sequences of characters, in this example it's ABC, then we reduce the shift amount by the corresponding prefix length. Let's go over another example to see how that plays out. Suppose the text is 3 dashes, ABC, XXX, AB, followed by a bunch more dashes. We'll reuse the same pattern string ABC, XXX, ABCY, as well as the previously calculated prefix length array. For illustration purposes, the pattern characters are included in the table. But when coding, you just use an integer array that stores only the prefix lengths. Nothing interesting happens during the first 3 characters. There is no match, so we just shift forward by 1 on each attempt. Then we'll start matching characters until we get to the second C character. Here we have a mismatch, having examined 9 characters. So now we'll shift the pattern string forward by this formula. Take the length of the examined substring and subtract the corresponding value from the prefix length array. In this case, we shift by 6. Let's continue with this example for one more step. Note that after the shift, the first 2 characters, A, B, are aligned. This is not a coincidence. It's exactly because of these 2 characters that we could not shift by an even bigger step. Note also that the index to text at which we are to do the next comparison is unchanged. Here, at index 11, an immediate mismatch occurs, but this time with the first C character. The prefix length array has a value of 0, so our formula yields a shift value of 3. Now that you have a sense of how the algorithm operates, let's take a look at an implementation written in Java. This is the first part of it that constructs the prefix length array. We create an array of length 1 more than the length of the pattern string so that we could store -1 into position 0. We then loop through each of the characters in the pattern string, incrementing the length of the prefix when the characters match. But if the characters don't match, then it is set to the value from the array at the corresponding index. Since the for loop executes only once, the running time of this subroutine is linearly proportional to the length of the pattern string. This is the implementation of the main algorithm, and it's based on a pseudocode taken directly from Wikipedia. It first calls the subroutine to create a prefix length array, and then iterates over the text characters, making comparisons. In case of a mismatch, it reassigns the index to the pattern string, P, based on what is in the prefix length array. Note that it's not until we get to the prefix length value of -1 that the index to text, T, is incremented. So indices T and P are both incremented with each match. But P is rolled back when there are mismatches. Since P can only roll back as much as it has progressed up to the mismatch, each character is examined at most twice, making this part of the algorithm linearly proportional to the length of text. Thus, the combined running time of this algorithm is order m plus n, where m is the length of the pattern string and n is the length of a text. A running time of order m plus n is as good as it gets. From the asymptotic analysis perspective, you simply can't expect to do better than that. This algorithm was invented in 1970s by Knuth Morris Pratt, yet to this day people are still working on this problem and coming up with better solutions. And for a good reason. These days in particular, there's a huge demand for processing unstructured text data in applications that involve neural networks and machine learning, which, by the way, has been an area of my work over the last several years. Working on these projects has led me to implementing some really interesting algorithms which, as you'd expect, will be topics of future episodes. That's it for now. I hope you've enjoyed this episode. If you did, please do click that thumbs up button. The source code is linked in the description, and if you have any questions or comments, please use that comment section. Thank you for watching.